events. So the premise here is that you will be informed, it'll be explicitly stated you are, and I'll put in quotation marks, so they might use a different word, selecting randomly n times. All right. So you're going to be doing something n times. All right. And in those n times, there are various different types. So for example, like in yesterday's problems, you were going to select 3. All right. The premise here is that you're going to have one selection and then you're going to multiply it by another times another. So each of the probabilities is basically be going inside of here. So the probability is going to be equal to something being multiplied by 3 times. Now, in most instances, there are only 2 possibilities. We refer to these as Bernoulli trials. And I was actually going to call today's lesson Bernoulli trials, but it's multiple independent events. All right. Bernoulli trials refers to the idea that there's 2 outcomes. They are independent, and we keep the same probability. Now, I know independent and same probability seem hand in hand in regards to it, but the probability of A is still the probability of A. Outcomes, sorry. Important note. There may be more than 2 outcome possibilities, but you will focus on just one as being a success. Others are failures. Hence, 2 outcomes, success or failures. In example, let's say we had let's say our sample space is A, B, and C. So these are the 3 different outcomes that can happen in a single event. All right. And you're going to do this, multiple times. So technically you can have A, you can have B, you can have, so you have the probability of A, you have the probability of B, you have the probability of C, such that, and actually instead of doing commas, if we were to add up all these probabilities, we would get 1. But we can break this down and instead call this the probability of A plus the probability of not A. And you might be asked only about A. Now the same can be done for asking about B or C. So you're either looking for we are interested in this example, only interested in A's outcome. So we either get A or we don't. And basically that's what happens with these problems. So even though might be more, and I might state more than one possibility, and as such give you the probability for that outcome, when the question gets asked, the question is going to be asked for either that one or not. Okay. As noted before, we would call this a success. You might see me see that, and this as a failure. You either get what you were looking for happens, or it doesn't. Most everything will be done as A and not A, and just as a reminder, the probability of not A is simply 1 minus the probability of A. So we're looking at those outcomes. Now, we're going to be doing something multiple times. We'll do, typically, like I said, we can, if we had, if we were looking, so I want to talk about tree diagrams very, very briefly here. It'll come up later on. Tree diagrams can help us look at the possibilities. So for example, if n is equal to 3, we could have outcome A or outcome not A. For this is your first time, and then we do it a second time and we have A and not A. And then we can have A or not A. So how many possibilities, how many different outcomes can we have for n equals 3 for Bernoulli? Have how many outcomes? We count the n's. So how many, so what we note here is that my outcomes could be A, 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 not A. I can get A, not A, 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 not A, not A. I can get not A, A, A. I can get not A, not A. I can get not A, not A, A, and I can get not A, not A, not A. So how many possibilities were there? We can just count them. 8. So there's 8 possibilities when n is 3. This is 8 is the same thing as 2 to the third. All right. Now, if n was equal to 5, there would be 2 to the 5th, which is 32 possibilities. Now, you don't want to list out all of those different possibilities, okay? So you're not, and the purpose is not to do that. Now, what is important here is that the probability of A and the probability of not A are the same throughout each of these. So a key understanding here is that if you remember, for Bernoulli, probability of A and probability of not A stay the same. All right. So in these questions, I'm going to ask you now, and this will be very important later on. Now, we know that all of these probabilities I'll actually do that a little bit later on. So if I wanted to find, so example, the probability of A, and this comes from like yesterday, would be the probability of A times the probability of A times the probability of A, which, as Anne had brought up during going over the homework solution, and as she feels comfortable, and you should have, and after today you need to, this would be the probability of A to the third power. Now, this is known as, all successes. So what's the probability that you have all successes? You get what you want every single time. Okay? It'd be A times A times A. The probability of A to the third power. If I said, what is the probability of not A, not A, not A? This is the probability of all failures when N is 3. So this would be the probability of not A to the third power. So in your homework, I might ask you, hey, what's the probability that you get all successes? Now, the word is not going to be success. The word is going to be like whatever A is. So, and I think, you might be looking for a certain blood type. You might be looking for a male. You might be looking for whatever it is. There's something that you're looking for and finding, and we're defining those ones as a success. And I think using example is bad. I want to change. I'm just going to change it to IE. Another IE. What is the probability first success is on the third attempt, the third selection? So what this means is that it's asking you what's the probability that you get, well, the first success doesn't happen to your third one. So what does that mean about what happened with the first two? What happened with the first two if your first success was on the third?
They were failures.
They were failures. So it's not A, then not A, and then A. And if you want to put commas here just to make sure that you're understanding what's going on here, that's perfectly fine. So this would be the probability of not A times the probability of not A times the probability of A. Now, when N is 3, you can write this out. But if N was like 12, you don't. So what that would mean is if you know how many, well, if the third one was the first success, then that means the previous two, the first two, were all failures. Times the probability of A. And you can actually technically think of that as probability of A to the first power. You could think of it as probability of A to the first power if you wish to. And that's very helpful, because if I look up here, two plus one equals 3, because N was 3. All right, that's just something to confirm, and that'll be more important later on. The most challenging problem, we'll get into some examples. So the most challenging problem, and this has its own type of problem. This is the probability at least one success. So let's think about the instance when N equals 3. Okay. We listed off all of the success, all the outcomes. We could have gotten, and I'm going to list them out again. We have A, not A, not A, not A, not A, not A, And you don't have to do this. You won't have to ever do this in the future. I'm just doing this one time. Not A, not A, not A, not A, not A, not A, not A. So the question I have for you is, which of these has at least one success? So the first one, does that have at least, how many successes does that have? How many successes happen in that first outcome? A, where A is defined as a success. How many successes were there? No. So it's success, success, success. How many successes happen in that very top one? A. We were looking for an A. We were looking for at least one A. How many A's happened?
Three.
Three. So there were three successes. Is that at least one success?
Yes.
Yes. Let's look at the second one. A, not A. Is there at least one success?
Yes.
The next one, A, not A. Does that have at least one success?
Yep.
The next one, at least one success?
Yep.
The next one,
Yep.
the next one,
Yep.
the next one,
Yep.
the next one.
That one too.
No. And actually, for the notes, I'm going to change the color on here. This instance has all failures, no successes. So, if I wanted to find the probability of at least one success, so if n is 3, then the probability of at least 1a, at least 1a, would be equal to the probability of A plus the probability of A not A plus dot 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 plus the probability of not A A. There would be 7 different probabilities to be able to do. There are 7 different. So if I asked you, hey, what's the probability of at least one success? Well, there's 8 different possibilities that can happen when n is 3. That means that there are 7 different outcomes. 7 of those outcomes will have at least one success. But there's a math trick. There's one instance that has all failures. There is one outcome that is not. Well, if I add those 7 probabilities with the probability of the in one single instance that doesn't happen, then what I get is that the fact that I would get I would get the same answer. So as such, we can take the complement to all failures. Mathematically, what I'm saying here is the probability of at least one plus the probability of none, no A, must equal 1. Not A, or at least one, 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 at least one. So those are all of the at least ones, plus the one single instance gives me 1. And that means that for n equals 3, the probability of at least 1A is equal to 1 minus the probability of no A's, which is 1 minus the probability of not A to the third power. This gives us the formula that if there are n selections, it doesn't matter if it's 3, 4, 5, the probability of at least one success is equal to 1 minus the probability of all failures to the nth power. Now, could you find all 7 probabilities and add them together? Yes. It doesn't make sense from a probability standpoint, though. So instead, what we try to do here is we just say, okay, at least 1 6, and this is, you'll see this problem pop up. And one, yes, 1 is also 100%. So remember, when we work in probability, we work in decimal forms. So probabilities add up to 1. It's the same thing as 100%. So you could do 100%, but that's why it's, because when you multiply, you must multiply the decimal number. So all failures. Failure, 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 failure. Now, think about it. Well, like I said, if n was 5, if we were going to do something 5 times, we said that there was going to be 32 possibilities, which means 31 of those possibilities have at least one instance of a success. And there's only one instance where you did not get at least one success. There's only one instance where you get failure, 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 and failure. If n was 5 and we did this A, not A, and we kept going and we kept doing all that stuff, I know it's kind of, I'm exaggerating here, but the point of the fact is that you would have only one instance of not A, not A, not A, not A, not A. All of these outcomes have at least one A, and this one has no A. There's only one outcome that has none. All right. Ready for example? All right, here. So in this example, let's state that, let's say that all of you have an equal chance of passing the AP exam, all right? Let's say all of you, I determine that every one of you has an equal chance, all right? A student has a 30% chance of passing the AP exam. Now, I could have also given you the percentages for a 1, a 2, a 3, a 4, and passing would have been if I added a 3, 4, 5. So let's say a student has a 30% chance of passing. Five students take the AP exam. What is the probability that A? What is the probability that all students pass the exam? What is the probability that all students pass the exam? Okay, so I've defined the success rate as 30%. So first off, I know that the probability of passing, I'll just call it S, is what? What's the probability of a student passing the exam?
0.3.
0.3. And what's the probability a student fails or doesn't pass the exam?
0.7.
0.7. Now that's for an individual student. So now we have 5 students that have taken it, 5 students who have taken it. So what is the probability that I get success, 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 success?
0.3 to the power of 5.
Perfect. And it's actually very low. All right, so it's 0.3 to the power of 5. Which is 0.00243. Now, this is also 0.243%, but we want to leave the answer as points. Don't change it into a percentage. All right? Don't change it into a percentage. So that's very small. There's less than half a percentage chance that if the probability of success was 30%, that all 5 students would pass. B. What is the probability that the 5th student is the only student to pass? Now I'm saying specifically that 5th student. So each of them is the first student, did they pass? The second student, the third student, the 4th student, and then the 5th student. Okay? So, in other words, I'm trying to find the probability of what happens. So what happened in the exam? What were the outcomes?
4 failures and 1 success.
So if you feel comfortable by writing the probability of failure here, and you want to say probability of F, and you feel comfortable with that, that's perfectly fine. Do it. All right. So failure is equal to the same thing as not a success. Failure, 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 and then what?
Success.
And then a success. Now, a lot of people have trouble, and the reason I did this is because, for example, when we're trying to do males and not males, or males and females, when you do this type of problem, you're thinking of males and then not males, okay? And then, which is really just males and females. So not a male means female. And remember, and I mentioned this yesterday in terms of how we discuss, for probability purposes, binary outcomes. So we just refer to it as male or not male, or female and not female. But as long as you understand that a failure is not a success and they're opposites, that's what's most important. So this probability would be what? I have 4 failures. I'll write it out. So I'm going to write it out this way. So it's the probability of failure to the
4th
times the probability of a success, which is
probability of 0.7 to
no,
the
no,
4th power.
you got to be careful there. You got to be careful there. It's not the probability of 0.7, it's 0.7. The probability is 0.7.
Oh, yeah. Sorry. 0.7 to the power of 4 times 0.3 to the power of 1.
Yeah.
Just 0.3.
Correct. So in our calculator, it's 0.7 raised to the 4th power times 0.3. And that gives me 0.07 and 203. If you just wrote 0.072, that'd be perfect enough. But if the number, would you write what you want, I will accept, 0.072. I could accept 0.07, but I like to at least see 2 numbers that are not 0 in my answer. That's just more of a preference. So now I want to point out this is specifically that that 5th student passed. I'm not asking you what's the probability that only 1 student passed. That's going to be coming from a later date. All right. I'm asking you for that 5th instance only. So I'm looking for a specific outcome. C. What's the probability that none of the students pass? What's the probability none of the students pass?
Just 0.7 to the power of 5.
Correct. It's failure, 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 failure. They're all failures. Which gives me 0.168. That's good enough. That's pretty actually highly. That's kind of likely. Now the probability that they all failed was like 0.00, or that they all passed 0.002, less than 1%, whereas all of them fail, there was a 16% chance. Now that's a wide swing, and that happens just because of the 30% success rate. So yes, you could say that's 16.8%, but in AP statistics and probability, we do not want to change it. And our final question, D. What is the probability that at least 1 student passes? Now, it could be that the probability that you get 1 success plus the probability of 2 successes plus the probability of 3 successes plus the probability of 4 successes plus the probability of 5 successes. You could do that. We do not want to do it this way. All right, because that's way too many different outcomes. There's 31 different ones. So when I see this problem that says at least 1, I got something that always helps me is that I try to do my Venn diagram, and then I do this, and this is fail, 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 fail. Mentally, this is what goes on in my head when I read that at one. There's all these different outways to get at least one success, and there's only one way to get a failure. All failures. So the probability of at least one success is equal to 1 minus the probability that we get all failures. And this is that big tricky type of one right there, that we get all failures.
Could we just take the answer from C and
Correct.
subtract it from 1?
Correct. So I did this problem in the notes. And now, not all the time are you given question C before you're given question D. I just want to point that out. But yes, we've already done the legwork on this problem. So this is equal to 1 minus 0.168, which would be 0.832. So if the probability of, if I had 5 students and each of those students had a 30% chance to pass the exam, there's about an 83% probable chance that at least one of them is going to come out with a passing grade, that I'll hear from one of the students that I passed the exam. Now, we have 17 students in this class. You know, basically in terms of the probability of any individual, you know, in reality, the probability of the chance of each of you passing is going to be different. But if we just look at it from a standpoint of each of you, you know, has the same one, we would get to this type of answer right here. That's the material. That's what we are doing. You have some probability questions like this. I did kind of want to bring, I want to talk about one of them is talking about, for example, donating blood, and you're looking for a specific type of blood. I think AB. So if you find AB, that's your success. And even though there's other blood types, we're only looking for either your AB or your not AB as your blood type. And I know there's positive, negative, and stuff like that, but we're just looking for a specific blood type and everything else. There's another problem that I think is a tricky one when you read it, and that is a problem that is based on the idea of traffic lights. So, you know, you're talking about the 5 days of the week, and it's 5, and the chance that you get a green light or get a red light. And so in that instance, you're actually looking for the probability, you're looking for getting a red light. So even though red lights are bad, that's what we're looking for. And so we're looking for, you know, what's the probability like at all red lights every day of the week? I got a red light at this specific stop sign. I can't remember the exact wording of the question. Then it would be the probability of a red light to the 5th power. What's the probability that the Friday was the first time that I did not get a red light? You know, those are the types of things that you would do. What's the probability that I got at least one green light? Okay, that's 1 minus the probability of all red lights. That's what I have for you for today. Homework is posted on Google Classroom. Have a good rest of your day.